Yeah.
Okay, can you tell John to join the classroom? And Paul, we need to set it up so someone we can share.
Are you plugged into the HDMI? Yeah, you should.
Yeah, how's your semester going?
So
I can give you the medium one. Check, check. This is you want to start playing it? Anytime there's something from your heart and this way.
Yeah, this is what I'll show.
Did you see the?
A friend will join on Zoom, but I think I can just click for him.
So I know the.
Jay Shi, John Shi,
Yeah.
SHI.
Really? Okay. Just let me know when you're ready for him to share, and then I'll ask
Okay.
you.
Okay. No, I'll share for him and click for him.
You don't like talking?
Yeah, he can just talk. It might be good if he is on this.
All of us are somewhere very silent of curriculum.
Reyes, I am here.
Oh, you're here. Okay.
Yeah, I was just
Like when I used to do construction, I used to wear crown.
This guy's
Yeah, it's like blue collar stuff. That's why I think it's like
He's seen it.
anytime I see it in there. Sorry?
He was seen it in the construction.
Yeah, so John, I'll click for you.
All right, sure, no problem.
Yeah, I did construction. I was like an electrician. I did some home renovations. Yeah, I've done a lot of stuff.
Obviously. And he started curriculum.
Yeah. Oh.
Later on, 2 weeks ago.
Yeah, that one hasn't settled in yet.
Yeah, that's the list of things. But yeah, I grew up on a beach in California and did like a lot of home construction and all that sort of stuff, like blue collar labor growing up. So anytime that I see like Carhartt in the student bookstore, I'm like, oh my God.
So where'd you build your own house today?
Would I build my own house? No, I pay somebody else to. Assuming I had money to buy a house.
My
You
dad,
have a good flight back?
Yeah, really? That's awesome.
I liked it too.
from scratch.
Oh,
I know it.
and so, oh, geez.
He finished building it, he met my mom.
Oh, geez.
He was like, he built the house.
Oh, it is a
Um,
good
They can hear me.
So what I'm hearing is if I want to get married one day, I need to go out and build a house.
From scratch.
He built the house.
Yeah, you're ready to go.
No, so can they hear me if I speak into the
I
mic?
guess you could do what I did. Just cut that.
Yeah, they can hear through the ceiling lights, and obviously clear if you speak. Is
But
that
then
cut
all
the
the
front
sound,
there?
the
or-
Okay.
noise, because
Very
he had
easy
4
to
doors.
discuss.
Oh,
Yeah,
see, I only
every
have one now, so.
Do we have one?
When is there?
It's gonna be again. It's next one.
Have you thought of the names yet?
I did, but I don't wanna tell anybody
No, no, no.
because
Yeah.
everyone has an opinion. And you're not
Thanks
changing.
for doing
it.
Yeah, no problem. Thanks for the opportunity.
You guys are the smart ones.
Okay.
Find a local expert.
True, true.
Not only he is.
Are you sure? Are you sure you want to decide on that? You're like,
That's just good. Okay.
See you in March.
I was so close to where you're today. This one, no, next.
Good morning, everybody. Morning. So, good morning and welcome to this last week of classes. We all know that the projects are due, the project and the evaluations will happen over the next week. So, today we have yet another guest lecture. Today's lecture is on graph neural networks. And I was debating on whether I should do the lecture myself or capture some experts on the subject. And so today we have two experts, Trish Chaudhary and John Shi. They are both, John Shi just graduated some time ago. Trish is currently a PhD student with Jose Mora. For those of you who know Jose, he works on graph signal processing. And these two guys, they are the local experts on graph neural networks with some very fancy recent work that they presented at ICANS. And so they are going to do the guest lecture for us. John is going to be on Zoom and he will do the first part of the lecture. And Shreyas is going to do the second part. So John, over here.
All right. Thank you, Big Shot. Can everyone hear me? Yes?
Yes.
Should we pause
Okay.
the poll now?
All right, good. Yeah, so
John,
yeah.
sorry, before we start, I think we should pause for like the class poll.
Attendance poll.
Attendance poll, okay.
Okay, no problem. Yeah.
Okay, post it here.
Yeah, yeah.
Perfect. So you can continue. That is square.
Okay. So my name is John Shi. I graduated in 2022 with my PhD. I do primarily graph signal processing theory. And my colleague Shreyas Chaudhary, you want to say something?
Yeah, I'm a PhD student with Jose. I don't necessarily only focus on graphs, but this has been, this is something that I've learned a lot over the last couple of years just through Jose and John's expertise. Yeah.
So we're here to present graph neural network. Next. So I'd first like to acknowledge our research team. We're actually very fortunate to have had 5 undergraduate interns, some great PhD students and postdocs as colleagues, and of course an amazing advisor, Jose Mora, that's supported us over the past, at least supported us over the past 7 years. And so this paper here is a paper we wrote for the Signal Processing magazine, I think in 2020. And it's written for the average reader, like I'm not an expert in our field, and I think it covers a lot of what we're going to be covering today. So yeah, here's the archive link. Next. So mainly in most deep learning applications, we focus on grid structured data. And what that means is it means data defined on a regular kind of lattice. So for 1D data, you can have a time series like this stock data here. That can be represented by this path graph with this loop around. And then for images is your 2D data. And so you have this image, and that can be represented by this grid here. And so primarily we focus, a lot of the work in deep learning has been done on this grid structured data. Next. However, as you can see here, the amount of unstructured data or data that's not really defined on a grid actually greatly exceeds the amount of structured data. And so our goal in these graph neural networks is to be able to extend these structured data algorithms like CNNs to be able to work on the unstructured data, of which there is considerably more. Next. And so we have data defined on an irregular graph. So these could be like knowledge graphs or citation networks. And basically, the idea here is that you have some irregular structure, which is represented by a graph, and then you have a signal on the graph, which basically means you assign a number or a vector to each node, and that represents your data. And so some applications are social networks, sensor feeds, web traffic, supply chains, and biological systems. So for example, you could imagine like you have a power grid, and each node would be like a power station, and they would be connected somehow, perhaps based on proximity. And then the signal would be like the voltage at each power station. And so by using a graph, we are able to represent this data defined on an irregular grid. Next. And so one of the main challenge of working with graph data is that when you're working with a grid, it has a fixed intuitive ordering. And what this means is this top left, we can consider the first pixel, like the first number, right? And then the bottom right is usually the last number. But and so it has this very natural ordering that basically like algorithms like CNNs kind of exploit. However, with a graph like this, you have an ordering problem, right? So which node is node 1? How do we compare different graphs and signals? And so we have this ordering problem. And the second question is, how do we actually incorporate the graph information. Next. And so, for example, we have discrete signal processing, or DSP, and this works well on time and images, right? You can take a Fourier transform, you can do convolution, stuff like that. However, when you have a time series like this, it fails for graph data. And what that means is you don't have this fixed ordering and like which node is the first node, and you also have no way to incorporate this graph data. Next. And so, like similarly with a classical CNN where you have convolution, pooling, and fully connected layers, it also only really works for grid structured Euclidean data. So it fails for graph data, right? And so you can imagine like if you had a graph here, it'd be hard to kind of make that into like a grid or a vector to put through your CNN because again, there is no fixed ordering. And even if you did that and defined an ordering, you wouldn't be able to incorporate the graph structure itself because you'd basically be taking your graph and kind of forcing it into a grid. And so these are the types of problems when we try using these traditional algorithms like DSP and CNNs on graph data. Next. So let's talk a bit more about these two problems, the ordering and the incorporation of graph data. And so when we do ordering or deal with ordering, the operations need to be something called permutation invariant. And what that means is we want the operation to produce the same or permuted numerical results regardless of ordering. So if you look at these two graphs, here on the left, I've ordered my nodes 1, 2, 3, and here on the right, it's the same graph, but I've ordered my nodes with this bottom node being 1, this left node being 2, and this right node being 3. So the only difference between this graph and this graph is how I've done the ordering. So now I have a signal defined on the graph. So this is -5 here, and 6 and 10. And so I'm going to order it based on the order of the nodes. So here it's going to be -5, 6, and 10. And here it's going to be 10, -5, then 6. Can they actually see my cursor? Probably not.
Yeah.
Okay. Yeah. Okay, so then when we have these vectors, right, we can talk about different operations. So for example, the sum here, you just add up the three numbers, right? And so if you add up the three numbers here, you get 11. And of course, this operation is permutation invariant. So when you add up the three numbers here, you also get 11. And so this the sum is permutation invariant. It means that if I reorder my nodes and I reorder this S vector, the result is going to be the same. But then if we look at something like the first difference, like the first value minus the second value minus the third value, or this operation, then you get -21 here, and then you get 9 here, because in this case, the subtraction, the order matters. And so this is not permutation invariant. And so you can imagine that if we had a deep learning algorithm that used something like this operation, then then if I had the same graph, but the ordering was changed, that would be a big problem, right? Because we might classify it differently based on this ordering. And lastly, you can have a ReLU, which will just zero out this -5, and you can see that these two are just permutations of each other. And so that's also going to be permutation invariant. So permutation invariance is actually very important. And so so it can either refer to getting the exact same number or the exact same result, or getting the permuted version of the same result. But what we don't want is we don't want this first difference case where you get completely different results based on how you order the nodes, right? Because if you have two people and they order the nodes differently, you want them to get the same result, or at least a permutation of the results. Next. The second issue is incorporating this graph data. So if you notice on the last slide, in the previous example, none of these operations actually use the graph. And so if I have this graph and then, I have the sum, the first difference, and the ReLU, I would get the same results even if there was no graph, or if the graph was different. And so that means that these operations don't really consider the graph, And so really we're just operating on a vector and we could use a CNN. So we're not really incorporating these connections here with these operations. Next. And so the main question for today is, how can we design deep learning techniques for graphs? And so we have to be able to incorporate the graph information somehow. And all the operations must be permutation invariant. And so this field is called geometric deep learning. Next. So I come from graph signal processing. And so a lot of what graph signal processing tries to do is similar to what I just talked about, except that it's not exactly deep learning. It's more machine learning. And so discrete signal processing works well for grid structure data. And graph signal processing tries to take everything you do in DSP, but apply it to graph data. And so essentially you have this graph and its adjacency matrix. And something interesting to note about this adjacency matrix is that in GSP, or where the ones occur in the adjacency matrix is actually switched or actually transposed from what you expect in computer science. So when you learn in computer science, like let's say 2 goes to 4, you should have a 1 here, right? Because it's row to column, node 2 to node 4. You should have a 1 here. But in GSP, we actually do the transpose of that. So that value would be here, I think, or here. Okay, this might be a little bit off, but it should be here. Yeah, there should be a 1 here, I think. Yeah. So it should go from column to row. And so if you're looking at some of these and it's a little bit off what you're used to because of computer science, it's because the order is column to row represents an edge going from column I to row J. And so if you're interested in learning more about graph signal processing, Jose offers this course in the fall, which is Special Topics in Signal Processing, Graph Signal Processing and Geometric Learning. Okay, next. And so in DSP, we assume the signal is periodic with period t. And so we have this path and this boundary condition. So you can imagine 4 numbers being repeated, like 1, 2, 3, 4, 1, 2, 3, 4. And that's represented by this time graph and then this path. And then the last value will wrap to the first. So you'd be like 1, 2, 3, 4. And then you cycle back 1, 2, 3, 4. And so you have this adjacency matrix. And then with GSP, it basically extends DSP by saying, hey, instead of using this specific time graph, we're going to use a general graph. And so this adjacency matrix would be an arbitrary adjacency matrix. And then the graph signal is found by assigning a value to each of the nodes. And so these values can represent the attributes on the knowledge graph, the measurements on the sensor network, or the voltages on the power grid. Next. And so a very key operation in signal processing is something called a graph shift. And so when we do it in DSP, it's a time shift. And so it's using this adjacency matrix. So the graph shift is going to be this adjacency matrix times the signal S. And so in DSP, it is simply going to shift the values down by 1. Or up by 1. So you see how here we have 2, 5, minus 1, 10. And then when I apply this adjacency by doing AS, it becomes 10, 2, 5, minus 1. So the value just shifted over by 1. However, in GSP, this is an arbitrary A representing the graph. And so when I shift, I still do AS, but instead of shifting along the path and wrapping around, like here, it shifts along these values. So you can imagine the AS in GSP as the value at 1 here sending the value from 1 to the other along the edges here. So it would go, so this value 1 would send to 2, 3, and 4, and then 2 would not send anywhere, and then 3 would send it along its edges to 1 and 4, 1 would send to 4, and then 3 would send to 4. So by doing this, the AS, you would get a different result, obviously, from DSP. And so this incorporates the graph structure. So this AS operation manages to capture the fact that this graph is different from this graph. And so now we want to look into permutation and variance for the graph shift. Next. And so for permutation and variance, right, we want to show that if I permute the nodes here, so I make the I commute the nodes, so I had 1, 2, 3, 4 here, and I have 1, 2, 3, 4 here, that I should get a permuted value. And so here, if I permute the nodes, I get S2 is -1, 2, 5, 10. When I apply the new permuted A2, I would get a permuted version of the shifted values. So this AS and this A2, S2 are permutations of each other. And note that they're permuted the same way that the S and the S2 were. And so when we talk about permutation and variance, when we change the ordering, it not only affects the A, but also affects the S. And so this operation is permutation invariant because AS and A2, S2 are permutations of each other. Next. And so to maybe formalize this into a proof, there's something called a permutation matrix, which is represented by this capital pi, and it's obtained by permuting the rows of the identity matrix. And so every permutation matrix is orthogonal, which means its inverse is simply its transpose. And so if you look at this S signal from the previous slide, if I apply this permutation matrix to it, pi S, I'm going to get S2. And so to show that the graph shift is indeed permutation invariant, what we do is we assume an A2, which is going to be a permuted version of the A1. And so this is going to operate on and reorder the rows of the A1. And this is going to operate and reorder the columns of the A1 in the same way. And so, and the signal itself is also going to be a reordered version of the S1. And so then all we need to really show is that by by calculating A2, S2 and substituting, this pi transpose and this pi will cancel, and you will get pi A1, S1. And so this is a permuted version of the original shifted signal A1, S1. And so therefore this line here shows that indeed the graph shift is permutation invariant.
Yeah, John, I think we're having trouble seeing your cursor.
Okay, that's fine. That's fine. Yeah, just yeah, maybe highlight this bottom line a bit. Yeah. Okay, so yeah, so A2, S2 is equal to the permuted version of A1, S1, which is what we just showed in the previous slide with the numbers. Next. And so now in GSP, GSP provides us with a linear shift invariant graph filter, which is a polynomial of A. So it's going to be a polynomial of A, which equals these coefficients times A to the I. And so it can be shown that this graph filter has max degree n-1. And so the reason why is because of something called the Cayley-Hamilton theorem, which says that a to the n can be written as a linear combination of the lower powers a to the 0 to a to the n-1. So if you have a to the n, you can just it's a linear combination of the lower powers, and so you can just rewrite it in terms of the lower powers. And so in GSP, all these polynomials of A have max degree n-1. And so convolution is therefore the matrix vector product of a polynomial of the adjacency matrix and the signal S. And then the graph Fourier transform, which I'll briefly touch on here, is found using the eigendecomposition of A. And so if you eigendecompose the A, the GFT inverse is going to be your matrix of eigenvectors. The lambda is going to be your matrix of eigenvalues. And to apply the Fourier transform to get S hat, you would just multiply by the GFT. Next. And so just to illustrate this point more, we can show that both convolution is permutation invariant and the GFT is permutation invariant. So like before, we're going to assume that A2 and S2 are permutations of A1 and S1. And so to show that the convolution is permutation invariant, we're going to calculate P of A2, S2, and that's good. And by substituting in and factoring out the pi and the pi transpose, you can see that the pi transpose and the pi is going to cancel. And so I end up with a permuted version of P of A1, S1. And so therefore the convolution is permutation invariant. Similarly, you can show the GFT is permutation invariant. So if you take the eigen decomposition of the A1, you get GFT1 inverse lambda 1 GFT1. And then if you assume A2 is a permutation of A1 and substitute, you'll get that the GFT2 inverse is a permuted version of the GFT1 inverse. And so therefore S2 hat is equal to S1 hat because these pi transpose and pi are going to cancel. And so this means that, so these are two different types of permutation invariance, right? So if I do the convolution, I get a permuted version of the original convolution. But if I take the GFT, regardless of how I permute, I'm always going to get the same signal, not a permuted signal. Next. And so now I'm going to briefly go over the graph neural networks types of experiments. And so today we're going to focus on two different types. The first one will be node classification. So a node classification is you're given a graph with nodes, and then the goal is to classify each node in the graph. And so the graph shows the connections between each data point. And so you cannot do pooling because if you pool, you're going to shrink the graph, and therefore you cannot classify the nodes. So you can think of node classification like you have an image in a CNN, and your goal is to classify each pixel, not each image, but each pixel in a single image. For graph signal classification, the goal is I'm given a bunch of graphs and a bunch of signals on the graph, and our goal is to classify the entire graph signal. And so in the analogy, this is like I've given a bunch of images, and the signal would be like the RGB values on the images. And so the goal is to classify each image. So graph signal classification is more of what we're used to in like the CNN kind of tasks. And so the graph shows the connections between the features as opposed to the data points. And the graph can be different for each each data point that we want to classify, each graph that we want to classify. And you can do pooling in this case. Next. So to illustrate this more, we can discuss a citation network. I think this is a visualization of the Cora data set. And basically, here we have 7 classes, which are colored here. And so the goal is to classify the type of paper using the citation network, which is this graph, and a bag of words at each node, which is going to be the bag of words or the data for each paper. And so the connections here represent a citation, and it's going to be an undirected edge. So if I cite you, if my paper cites yours, then we're going to have an edge. And so our goal is to using the connections that which is the graph and a bag of words at each node. Our goal is to classify each paper into one of these 7 classes. And if you notice, something interesting about this graph is that the connections between these edges here generally connect nodes of the same class, which makes sense because if my paper cites yours, it probably means that we're in a similar kind of field, like physics or math, And so it's very likely for the nodes to connect using that and be of the same class. And so here we have three very commonly used data sets, CiteSeer, Quora, and PubMed. And here are some details about the number of nodes and classes and stuff like that. Next. And so a very interesting question that was brought up in a paper in 2018 was, why do we need a graph? Why not just use like an MLP or CNN or some type of classification thing? And so because like I could just take a bag of words and the class of each paper and just run an MLP. I don't really need the graph. And so the reason why you need the graph is because of this label rate here in the red box, where you see how in each of these tasks, only about less than 5%, a little less than 6% of these nodes are labeled, which basically means that the graph allows for a smaller training set. So if you were to train this with MLP, you'd have a very large training set and test set split. But here, because I have a graph, I only need about 5% of the of labeled data for my training set. And so in essence, the graph is like an answer key and it helps with the classification. So you can imagine, like, if you were going to take an exam, if you didn't have a graph, then you might have to do like maybe 10, like a large amount of practice problems in order to do well on the exam. And look at a lot of different examples, right? So like if it was like a math exam, you might have to look through like 1,000 problems in order to get a good score on your exam. But if I gave you the answer key, which is kind of like my graph, then you probably don't need to look at very many examples because you have a solution, kind of. You have the answers already. And so if you could reference the answer key, then you probably wouldn't have to study as much in order to get the same score. And so in essence, for these node classification problems, you can use an MLP, but the graph enables you to have a lower label rate. Next. And so a very interesting question, therefore, is how good is your answer key? Right? Because if you were taking an exam and you got the answers from a friend and they weren't very good, you're probably not going to pass the exam if you don't study. So, so the graph actually greatly affects accuracy. And so this is from one of our papers by Lavender Jang, and basically you can see that the test accuracy here for the Quora data set using the actual citation network is about 80%. But if I replace this graph with an identity graph or a random graph, which is the Erdos-Renyi graph, which means that I either have no connections for the identity case or I have random connections for the Erdos-Renyi case, you see that the accuracy drops by about 10, 15% over here, right? So basically, this means that the graph itself greatly increases the accuracy, and how good it is also really affects it. You can't just have any graph. Next. And so an interesting question, therefore, is how to form a graph. And so one way is to use some intuitive heuristic believed to relate to the classification. And so, for example, in the citation network, connecting papers that cite each other is a very common heuristic. And because we're trying to classify the paper type or the field that the paper comes from, the hope is that if I cite you, then we're probably of the same field. And another way to form a graph is to use some statistical methods like the cross correlations of the features. And so that will form a different graph than this heuristic. And so this is more statistical, but it may not be as intuitive as using some intuitive heuristic. And so this is not a very clear and obvious answer to how good is your like graph in node classification. Generally, you just have to run it. But some things that are considered are something called homophily, which is are nodes with the same classes connected. or high, which leads to high homophily. And so in your citation network, it has high homophily because generally when two nodes are connected, they're probably of the same field, right? Because the papers cite each other. But if you look at a different case, like a social network, like if we're trying to classify users in a social network, if Shreyas is highly connected to all the other nodes, that may not mean he is the same class as the other nodes around him. And another thing to consider are features. Are nodes with similar features connected? And clustering. Are nodes with the same class clustered together? Are nodes with the same features clustered together? So you can imagine a very extreme case where you have class 1. Can everyone see me on the camera?
No.
Okay, so you can imagine class 1, which will be my left hand, and a bunch of nodes in class 1 and a bunch of nodes in class 2. And if class 1 is all connected and class 2 is all connected, but they're not connected with each other, then when I do the convolution operation, class 1 all becomes one value, and then class 2 all becomes a different value, making it very easy to classify. However, if all my class 1 values were connected to all my class 2 values, when I do the convolution, they're going to mix together, and it's going to make it harder to be able to distinguish between the two. And so all these features, all these factors about the graph affect the node classification accuracy, and it's very difficult to pinpoint one specific reason why these things happen. Next.
Okay. And we can see now, by the way, John, just so you know.
Okay, good. Yeah, okay. So and so now we're going to talk about graph classification. So graph classification is when I'm given a graph and my goal is to classify a bunch of graphs, and my goal is to classify each graph. So each protein, chemical, or enzyme is a different graph. And then data is the elements of each node in the structure. So you could label the hydrogen as 1, and you could label the carbon as 2, and so on. And so given this graph and the signal, which is the atom type of each node, each molecule, the goal is to predict the properties based on this chemical structure. So mutag, for example, is predicting whether a given chemical is mutagenic. And enzyme is whether I think it's one of 6 proteins, or yeah. So basically, I'm given a bunch of these graphs, and so my goal is to classify each graph into whether it's mutagenic or whether it's an enzyme, stuff like that. Next. Another example is the IMDb binary and Reddit classes. And so the IMDb binary is I'm given a bunch of actors that are connected in a network based on who appeared in what movies. And so the goal is to classify this Titanic movie, for example, as action or romance movie. So I'm given these connections with the actors, and my goal is to classify the movie. And for Reddit, the goal is I have a social network and or the posts of users in a social network. And so for each user, I generate a different graph connecting the posts that the user has together. And so my goal is to predict whether this user comes from a Q&A forum or a discussion forum. Next. Okay, and so as we can see, GSP is about transforming DSP into GSP. And so now we ask, how can we change this CNN architecture to work with graph CNN? Next. And so just click through, Shreyas. And so the next thing is that traditional CNNs do not work well on graph data. And so we ask these 4 questions. And so we already discussed what graph problems can be solved. And in the next section, Shreyas is going to talk about the graph convolutional layers, graph pooling, and which graph architecture should be used. Next. And so I'm going to pass it to Shreyas.
Yeah, so I'll talk more about the specifics about like how graph convolutional neural networks actually work, and hopefully after the next few set of slides, you will be able to code these up too on your own if you want to. So just to give you a high-level overview and to summarize basically what John said, we have a few sets of. Is that better? Better? Okay. Yeah, so we have like a few sets of different problems that we can look at. The first and probably the most standard is graph classification. So the idea there being that we have a data set of graphs. The graphs can have a variety of different number of nodes. We don't assume that the graphs have the same. Oh, okay.
It's just not, it's not picking up your, it's in a weird position.
Oh, okay. 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 Is that better? Good. Okay, okay. Yeah, so in graph classification, we have like a bunch of different graphs or a data set of graphs. The graphs can have a varying number of nodes, and the idea is just that we want to classify the graphs into different classes. So the output of the graph convolutional neural network will just be a vector, y hat, which is standard, like our standard one hot vector indicating which class the network belongs to. Similarly, we can define a problem of graph embeddings, just like we want to learn maybe embeddings of images. Maybe we want to learn an embedding where graphs for certain types are closer together in terms of some metric and some embedding space. And finally, we have node classification, where the idea is that we have this graph here, and we want to output, we want to keep the graph structure, but basically assign a label to each node in the graph, as shown here. So in order to represent the graph as an input to the graph convolutional neural network, we typically represent it using the adjacency matrix, which again will tell us which nodes are connected to which other nodes. And we'll also use the node features. So each of the nodes in this graph over here will have a number or a vector assigned to it. You can think of this, as John mentioned, as either being maybe like a bag of words representation in a citation network, or maybe like a measurement in a sensor network. And the matrix X here collects these node features along the rows. So X here is a matrix where the number of rows is the number of nodes in the graph, and each row is a vector of dimension p, where p is like the size of the vector at each node. Yeah, so here's a high-level overview of how graph convolutional neural networks work. And to be honest, they're very similar to normal convolutional neural networks. The only difference is that we replace the standard convolution over images with graph convolution. So we have like a series of graph convolution here, followed by a nonlinearity of our choice, followed by more graph convolutions, followed by another nonlinear activation, and so on and so forth. So for problems where we want to assign an embedding or label to each node, we usually stop after we get to this point. So after we do a series of graph convolutions and nonlinear activations, we still have the graph structure, but at that point we have like a vector assigned to each node. If we want to go further and do graph classification, then we need to somehow aggregate the representations over all the nodes and use that to basically learn a graph embedding, which we can use for downstream graph classification or other like downstream global graph tasks. Okay. So the main motivation, and John touched on this a bit, so I won't spend too much time on it, for why we need specifically graph convolutional neural networks instead of just using MLPs or standard CNNs, is that graphs themselves can be represented in a variety of different ways, meaning that if I have a single graph and I send as input to the graph convolutional neural network, that graph, in terms of its adjacency matrix and its features, I can represent the same graph in a variety of different ways. The representation is not unique. So for example here, we have this what's called a star graph, where I've labeled the nodes as 1, 2, 3, and 4. And this is the corresponding adjacency matrix. And this is what the node feature matrix X would look like here. So the number of rows in X would be 4, and each row would be a vector corresponding to the value at a given node. But this graph is the same as this graph over here on the right-hand side. And you can see that the representations or the inputs to the graph convolutional neural network are different, right? Like the A matrix looks different than this A matrix, and the X matrix looks different than this X matrix. So we want the graph neural network to be able to still assign each node the proper label in the node classification task, or assign the graph, the same graph label to both of these graphs. And that's where graph neural networks really come in. Like the implicit bias here that we have with graph neural networks is this idea of permutation and variance, meaning that if we reorder the nodes from this to this, the output of the graph neural network stays the same. That's the main idea. Okay. And yeah, so now I'll get into more of the specifics of graph convolutional layers. The idea or how graph convolution works in practice is actually very simple. So all of the graph convolutional layer architectures that we'll look at, and actually most that have been proposed to date, have this general structure or have this general setup. So the first thing we do is, let's say we're starting here at a given node I in the graph. This node I has some representation associated with it. This could be like the initial set of measurements, or it could be like the node embedding at a given layer. What we do is we look at all of the nodes connected to I, and this is called the neighborhood of I, which is given by the calligraphic N of I. So the neighborhood of I is shown in green over here, and we somehow aggregate the representations over the neighborhood to get a single vector. And that aggregation step yields this vector bold AI here. And this aggregation function can take on a variety of different forms, and the architectures that continue to be proposed today basically just propose different ways by which to do this aggregation, or smarter ways by which to do this aggregation. So after we aggregate the representations over the neighborhood of a given node I, what we do is just simply combine that aggregation to the representation that was already present at node I, and that's the combining step. So here we combine xi, which will be the representation or the vector that we had at this node, with the aggregation from the neighbors in order to get a new representation at the given node I. And then we'll propagate this representation downward through the subsequent layers. So one step of graph convolution, or one layer of graph convolution, will basically just do these operations at each node in the graph simultaneously. So here we're just considering a node I and doing this aggregation and combining step, but we'll also do it for maybe this node, like all of the nodes in the graph simultaneously. So here we can look at a very simple graph convolutional layer just to start. The weight matrices shown in blue are what are learned at the layer. So this is kind of like just a generalization of a linear layer. And we can see on the right-hand side, this term here is the aggregation function. So what we're doing is we're looking at all of the neighbors for a given node I, and simply taking a weighted sum, where the weight is given by the edge weight defined by the adjacency matrix. And after we take that weighted sum, we multiply it by a learned matrix, W2. And this gives us the aggregation vector AI from the previous slide. And the combination step is simply just to linearly transform the current representation at that node xi and add it to the aggregation vector. So in order to implement this, we usually vectorize it because, again, we have to do this for all nodes I in the graph. And in code, if we want to do this for all nodes I in the graph, and if we do it in a for loop, the graphs are very large, and well, the for loop will take forever to run. So we usually vectorize it. And here's the vectorized representation. So again, capital X here is going to be a matrix where the number of rows in the matrix is exactly the number of nodes in the graph. And this won't change. The layer doesn't change the number of rows in the X matrix. But it will change the number of columns in the X matrix, which is, you can interpret as the number of features that you go from layer L to layer L plus 1 with. And A here is, again, the weighted adjacency matrix. So this is one, we can think of this as one graph convolutional layer. And after this, you would do a nonlinearity like a ReLU, TANH, or softmax, and you would get, and then you could do another graph convolutional layer, and you would get another matrix like this with the same number of rows but a different number of columns, depending on the dimensions of the W1 and W2 that you set. Yeah, so earlier in the class, I'm sure you guys probably covered how normal convolutional neural networks are kind of like scanning MLPs, right? So graph neural networks themselves are actually just, you can think of them as distributed MLPs in a sense. So the interpretation here is, like, let's say we are at a node I, and x0 is going to be the vector assigned to node I at the start. So this is something that we have from the data itself. So if we look at how this graph convolution works, we multiply xi by w1, the first weight matrix at layer 0. And we also add in this term, aggregation at layer 0, which is essentially just this term on the right-hand side. But if you notice, like, this architecture in the pink box is just an MLP, right? We have a series of linear layers, which are indicated by the blue boxes, and the green boxes are just biases, are just bias vectors, which are obtained through aggregation of the neighboring nodes. So if we look down at the bottom, what's happening is we do one step of aggregation, or we can think of it as doing one step of message passing with your neighbors to obtain the aggregated representation over the neighborhood. And then you can think of it as doing as performing one linear layer of an MLP, and you basically just repeat these steps until you get the output node representation of the entire neural network. Okay. Yeah, so the architectures here are just different methods by which to do graph convolution. And again, they still follow the same approach of doing aggregation and then combining. So we'll first start off by looking at the GCN architecture. So the convolutional layer in GCN is defined similar to the simple convolutional layer we saw before, but it's defined as this, where the A hat is still the adjacency matrix of the graph, but we add self loops to each of the nodes. So A hat is just the original adjacency matrix plus the identity matrix. And the matrix D is the degree matrix of A hat. So you can think of this as just taking a sum over all the rows of A hat. And this operation here, if we want to look at it for a specific node I, we can look at the expression up above. So here we do the aggregation by taking a sum, a weighted sum, over all of the neighbors. Sorry, there should be a subscript J here, where the weight is determined not only by the edge weights of the adjacency matrix, but also the degree. So it takes into account how many neighbors node I and node J have. And the reason why we usually take into account the degree information, or why we have this like d to the minus 1/2, a d to the minus 1/2 here, is that it, in a sense, normalizes the eigenvalues of the adjacency matrix. So we call this sort of matrix a normalized adjacency matrix. And the maximum eigenvalue of the normalized adjacency matrix is guaranteed to be 1. And you may ask, like, why do we normalize? Well, if we look at, a standard graph convolutional neural network, with several layers, but let's just for simplicity ignore the nonlinearity. We can see that the expression looks something like this. So just imagine we have this expression here, but we compose this with many other similar convolutional layers. The expression looks something like this, where we have the adjacency matrix to the power L times x0 times all of these weight matrices that are learned at all of the layers. Okay? And if we take the eigendecomposition of the A matrix, we can see that A to the L is just going to be the eigenvalues to the Lth power. Now, if the eigenvalues do not have like a maximum value of 1, if the maximum eigenvalue is not 1, then this matrix is going to blow up and it leads to computational instabilities during training. So that's why most architectures nowadays, they normalize the adjacency matrix to have maximum eigenvalue of 1. Okay. So the TAGCN was actually proposed by our group in 2018. You can see it very closely resembles the standard graph convolutional neural network, which was proposed in 2017 by Kiff and Welling. But we have this term K. We have this summation over K here, that being the difference. And K is a hyperparameter that you set for a given layer. The idea of the term K here is to well, what K actually does here is it allows you to incorporate information from neighbors that are more than just one hop away. So if you look at the expression for the normal GCN, we see that we only incorporate information from the neighbors of a given node I. But TAGCN, if we set K equal to 2 or 3, will allow us to look at all of the neighbors of the neighbors, and the neighbors of the neighbors of the neighbors, and so on and so forth.
You don't have weights with the polynomial terms?
In the TAGCN? Yeah, so we have a different weight matrix here, WK, for each power. Yeah. So we'll weight the neighbors different from the neighbors of the neighbors. And there's another slide on this later if it's not clear right now.
So the weight matrix, say for K1, that's the immediate neighbors. For K2, that would be the second neighbor, but not the immediate neighbors?
Yeah, exactly. Okay. Yeah, so here we looked at, we did some very basic analysis of why we should normalize the adjacency matrix, but we can also use the same framework to look at what happens in general when we have very deep graph convolutional neural networks. So there's this problem with graph convolutional neural networks, which is known as the oversmoothing problem. The main idea is that if we have very deep graph convolutional neural networks, the accuracy after a certain point drops. So here we have on the x-axis of this graph the number of convolutional layers in a graph CNN, and the y-axis denotes the accuracy on classifying the Cora dataset. And you can see after about layer 4 or even 5, the accuracy drops significantly. So now we want to maybe study why does this happen, and we can use the same analysis as before. So here we have the representation for a graph convolutional neural network with all of the layers composed, but just for simplicity, ignoring the nonlinearities. If we look at this and take the eigendecomposition of A to the L, this term, which is the eigendecomposition of A times x0, actually converges if you have L to a high enough power to the dominating eigenvector of A. So really, as you increase the number of layers, this term, when in the blue section here, will converge to a fixed vector, which we know a priori. So that's gives some intuition for why this oversmoothing problem happens, and it's actually still an open research question for what we can do to mitigate this problem in deep GCNNs. Okay, so yeah, going back to the TAGCN, this maybe can give a little more insight into what is happening. So K here will give you the number of hops away from a given node from which you can incorporate information. So let's say we set K equal to 0 here. What we're doing then is just not really incorporating any information from the neighbors at all. If we set k is equal to 1, then we incorporate information from the node itself and also the nodes that are one hop away from this given node. And then for k is equal to 2, we look at information from all nodes that are 2 hops away from the red node here. Okay. So up until this point, all of the neural networks or graph convolutional layers that we've looked at assign an equal weight or just use the fixed edge weights of the original adjacency matrix A. But in some cases, there may be graphs where maybe you want to learn like which weights or which nodes you should weight more than other nodes. So for example, if there's a noisy graph, it doesn't make sense for us to weight each node according to the weighted adjacency matrix. Maybe we want to weight some nodes less when doing the aggregation step and some nodes more. And this is essentially what the graph attention convolutional layer enables us to do. So let's first look at this expression here, which we can again recognize as doing some sort of aggregation step followed by a combining step, where the aggregation step uses these learned weights, alpha ij. And the alpha ij are the attention weights that basically say how much we should look at a certain neighbor when we are aggregating over the neighborhood. So in order to compute the attention weights, what we essentially do is for a given node I, whose representation we want to update, we concatenate that representation with the representation of a neighbor. And then we multiply the concatenated vector by a learned vector A here. And this gives us, after we pass it through like a leaky ReLU, this gives us what we call alpha ij. And we do this for all neighbors of a given node, and then we take a softmax over the number of neighbors. So when we take softmax over the number of neighbors, that means we assign, like you can maybe think of it as a probability distribution over all of the nodes connected to node I, and the strength of the attention weight to a given neighbor will tell you how much you should look at that neighbor when doing the aggregation. So because now we have defined just standard graph convolution or standard graph attention, we can also consider multi-head attention, which is basically just doing this attention several times. So using many different weights, alpha ij. So if we have like, if we do this attention operation, let's say 3 times with 3 sets of weights, alpha ij, then we have multi-head attention with 3 heads. And we can either concatenate or average the multi-head attention representations to get an aggregated representation of the neighborhood.
So, do you really need the leaky ReLU inside the logic, or is that just an engineering choice?
Yeah, the leaky ReLU is not necessary. It's an engineering choice that the authors say works better than not having the leaky ReLU. And yeah, actually there are now like several different flavors of graph attention which don't necessarily look exactly like this, but are similar. But this is one of the first approaches, so we're just covering it that way, yeah. Okay, so after we do a series of graph convolutional layers and nonlinearities, we still have the original graph structure, and we have assigned now at this point a vector representation to each node in the graph. So up until now, the output of the graph neural network is going to be an n by c matrix, where C is the output feature dimension of the graph convolutional neural network. Now, if we want to classify the entire graph itself, we somehow need to aggregate all of the node representations into a single vector so that we can obtain a graph embedding by which to classify the graph. But we want to somehow do this aggregation in a way that one is permutation invariant. So if the nodes are reordered, we still want to obtain the same graph representation. And that's why if we just concatenate all of the node representations that we have obtained from the neural network up until this point, we won't obtain anything meaningful because the concatenation operation assumes some sort of ordering on the nodes. So the idea here is to look at how can we somehow like collapse this nodal dimension n in a way that is permutation invariant. And it turns out there's very simple methods by which to do this. So one method is so-called global add pooling. The idea is just you take a sum over all of the node representations in the graph. So if each node has a representation of dimension c, and there are n nodes in the graph, then just by summing over all of the nodes in the graph, you have obtained a single representation for the entire graph of dimension c. And that representation is permutation invariant, because if you reorder the nodes in the graph, just like taking a summation over the nodes will not change the representation you obtain. Similarly, we can do global mean pooling, which is the same as global add pooling, but you average by the number of nodes in the graph, and global max pooling. The idea of max pooling is if we stack all of the node features in an n by c matrix, we just take the max operation over the rows. We just do a max over the rows to obtain a single c-dimensional representation for the entire graph. So Mark, who was a PhD student in our group, studied how these different global aggregation methods actually impact graph classification accuracy. And the main takeaway is that the global aggregation method that you use is generally dependent on the data set that you're working with. So maybe for the sake of time, we can skip that. Okay, so now we'll briefly go over some graph pooling methods. The idea of graph pooling is similar to the idea of pooling in convolutional neural networks, where there we want to somehow downsample the feature maps in order to make the computations less expensive. But for CNNs, it's usually easier because we have this fixed ordering. We can slide here like a standard 2x2 kernel over the entire image to downsample it through like a max pooling sort of operator. But for graphs, it's not really clear, like how can you sort of downsample the graph in a way that still maintains the meaning of the graph itself. Yeah, so this is exactly the problem that graph pooling aims to solve, which is we have some graph structure, but we want to shrink the size of the graph so that the downstream layers don't have to use all of the nodes in the graph for the computation. But how we go from this graph on the left to the graph on the right is not always clear. So this was one method that was proposed in 2018. It's called top K pool. The idea here is, again, we have the adjacency matrix and we have the feature matrix X. So in order to learn or this method essentially learns which nodes to ignore as you move from layer to layer. And it does that by first taking the feature matrix X and it multiplies it by a learned vector P to obtain a representation Y. And then it simply finds the top K entries of this Y vector. And those top K entries, the K being a hyperparameter that the user sets, and that's kind of similar to like the window size or of pooling in standard CNNs. So after we select the top K entries of this Y vector, we use it to mask out the entries of X and A that are not relevant. So we only keep the top or the indices corresponding to the top K entries of the Y vector. So that's what we see in this matrix here, where we've masked out the second and fourth row. And that's what we see in the corresponding adjacency matrix too. We've masked out all of the connections corresponding to node 2 and node 4. And after that, it just multiplies the new representation X by a learned matrix Y, or sorry, Y is a function of the original Y here, and then we obtain like a downsampled version of the graph that we can pass down to the downstream layers of the GNN. So this entire operation has converted the graph, which originally had 4 nodes, to a new graph which now has 2 nodes.
Basically trimming out nodes in there.
Right, exactly. Okay, so
So that's more like a pruning operation than pulling, right?
yeah, so yeah, we can think of it as like a pruning operation also, or so for graphs in general, it's not clear like how we can downsample the graph, and John has been doing some research on this that maybe you can touch on later. But it is similar to kind of doing like a max pooling in some sense, because you still take into account here some of the information over the neighborhood in order to identify which nodes to drop.
Can attention be used here, like we previously calculated the attention? We know which nodes are more important.
Yeah, so there is this other method exactly that proposes like using self-attention for graph pooling, and the idea here, it's very similar to this method, but we replaced like the learn projection P here with like a GNN, and I think maybe like it's not clear here where the self-attention weights come into play, but you could definitely incorporate like self-attention weights on identifying which nodes have weak connections and therefore or which nodes to drop in the downstream layers. Yeah. So maybe I will skip this for now to come back to it. Okay. Yeah, so if you want to code graph CNNs, I highly recommend you check out this library called PyTorch Geometric. It has implementations for all of the standard graph convolutional layers that we looked at, and it enables you to batch graphs of different dimensions. It handles all of that for you on the back end. And it also enables you to define easily your own graph convolutional layers and your own pooling layers if you want to try out different strategies for doing these operations. Okay, and so I'll also briefly talk about this work on, or this recent line of work on how expressive graph neural networks actually are. So this was in a paper from 2019, which studied ways in which the aggregation operation of graph neural networks fail. So let's look at, like, let's say the first picture here. If we aggregate or assign a new node embedding to this node, the center node here, that is the mean of its neighbors, this graph and this graph produce the same embedding for the center node, using both the mean and the max. And the same thing happens in these graphs here. So like if we assign a new node embedding to V by taking the aggregation operator to be the max function, we can see that taking the max of the neighbors here produces the same aggregation operator as taking the max of the neighbors here.
What do the colors mean?
The colors would be values, yeah. So maybe green is bigger than red, red bigger than green. Just to indicate that they're different, yeah. So the main message of this top line of charts is that there are cases where you have different graph structures, but the aggregation operator fails to distinguish the graph structure or fails to take into account that graph structure when you update the node representation at the center node. And we also see that this happens in, like, not these sort of made up cases, but in real world data sets. So for example, here we have a molecule on the left called decalin, and we have another molecule on the right, but these graphs are more or less isomorphic. So this same sort of problem that occurred here using both the mean and max aggregation also occurs here, where although the graph structures are different, the node embeddings, or although the graph structures are different, the node embeddings come out to be the same. So one of the interns in our group looked at how we can alleviate this problem by using what's known as a spectral shift matrix, which comes from graph signal processing theory. And the idea is that even though doing aggregation using the normal adjacency matrix A may be susceptible to some of the problems we saw on the prior slide, using the spectral shift operator, doing aggregation using the spectral shift operator, in addition to the A, will allow us to distinguish the graph structure better. So here we have some results on a synthetic data set where we just use the A matrix, which is the standard adjacency matrix, and we also use the spectral shift matrix. And the last column is using a new sort of shift matrix that is defined by taking a sum of the adjacency and the spectral shift matrix. And you can see in both cases, if we apply GCN and TAGCN using the A plus M matrix, the performance is better. Using the M or the A plus MM matrix, the performance is better.
So what exactly do you mean by spectral shift?
So the spectral shift is kind of like the shift in the spectral domain. Just as the adjacency matrix, we can think of it as the shift in the nodal domain.
So now I'm gonna talk for the rest of this talk, I think. And so a case that so clearly from Shreyas's and my explanations, CNNs are GNNs. CNNs and GNNs are very different. But we actually gave this talk in South Korea at ICAST last Thursday. And so we actually can show theoretically that, in fact, they're actually not very different. And GNNs and are CNNs plus boundary conditions. And so we're going to briefly, since we're kind of short on time, quickly highlight some of the ideas. And so this combines my work on my thesis work on GSP with GCNNs. And so this is the citation. And I also sent the paper to Big Shah so he can post it. But yeah, next. And yes, hang on, go back one. Yeah, yes, this does mean that we just got back from Korea last night and we are very, very tired. Okay, keep going. Yeah. So as we know, GNNs and CNNs are very different, but next. Actually, if you take the CNNs and if you take the GNN and convert it to another domain, this CNN, you can show that it is indeed equivalent to a 1D convolution. Next. And so the idea here is that with GSP, you have this arbitrary graph. With DSP, you have this time graph. And so for my thesis, there's something called a companion model, which basically is kind of in the middle here. And you can see that the shift, that this like arbitrary shift in the GSP becomes this companion model it becomes like this graph in the companion model. And so this companion model graph resembles DSP. It looks like the path, which is shown in blue, and then the boundary condition. And so from here, we can show that in the companion model, GSP can be considered as DSP plus boundary conditions. Next. And so very quickly, next. Let's tap through this. Okay, so basically the idea with the companion model is you have this delta zero, you shift it using the A, n minus 1 times, and then you linearly combine them to form the signal S. And this is the graph signal that is given. And so by transforming the S using these and writing it as a linear combination of these basis vectors, we obtain this the weights P, and P is going to be the vector of these weights. And so the companion signal model uses this P instead of using the S. Unlike graph signals, the P actually can be proven to have a fixed ordering and is permutation invariant. And so the key idea of the companion signal model is when I do this AS, or when I do what Shreyas was calling the aggregation in GSP or a GCNN, it is equivalent to CP, C comp P. And why is this important? Well, the C comp looks like this. And so this is the path plus the boundary condition. And you can see that if I shift along this path, it looks like the time graph. It looks like 1D time. And so therefore, if I consider the AS or the convolution operation in the companion model, I can view it as like a path. Next. Just tap through this. Okay, so next. So basically this is, so if I have the S and I convert it to the P, if I shift it once, it's going to become CP. And so the values are just going to shift down by 1. If I do A squared, it's going to shift down by 2. And only when I do A cubed am I going to hit this boundary condition or these red edges, and this P2 is going to redistribute into the values. So you can see that this looks like a normal time shift. Next. And so, yeah, just tap through this, please. And so as Shreyas went through, the graph convolution in graph CNNs for TAGCN is going to be this polynomial of A, and then for GCN it's this fixed kernel K A plus I, right? And this was the A tilde from the GCN architecture, and so you can see that it's just aggregating the neighbors. Next. And so you can prove that the TAGCN with polynomial degree k less than n is equivalent to a convolutional layer of a CNN with appropriate boundary conditions. And in fact, if the P has n minus d trailing zeros, then and this K is small enough, then we do not actually hit the boundary condition. Okay, in other words, if it's P0, I can shift it n minus d times before I hit this boundary condition. Next. And so to illustrate this, basically if I have this PW of A and I'm convolving using the neighbors, then this can be equivalent to W2 times this shifted P times plus W1 times this shifted P plus W0 times this shifted P. And this is simply a 1D convolution of the vectors P and W. And so this looks just like a CNN with a 3x1 kernel where W equals W0, W1, W2, assuming we don't hit the boundary condition. Next. So as we said before, GCN is a special case of TAGCN where the polynomial is just A plus I. And so clearly, just by applying that it's a special case and applying the previous theorem, we can show that the GCN convolutional layer is equivalent to a CNN. Next. And so to illustrate this, we have our filter, which is K times A plus I. And so you can see that this is K times the original P, which is this I, and then K times the shifted P, which is this KA. And so this is just like a CNN with a 2x1 kernel, except that we've restricted the kernel to have the same W0 and W1 weight. They're both going to be K. Next. And so here we designed an architecture called companion CNN, where we take the vertex representation, convert it to the companion representation, and then pass it through your traditional 1D CNN with the 1D convolution out of the box. And so an interesting thing is that we'll skip this next. Okay, so then we run experiments, and so the P is equal to this van der Maan matrix inverse S hat. And so the van der Maan matrix is going to be this matrix of the eigenvalues, where you take the eigenvalues and raise it to the 0th power, the 1st power, all the way to the n minus 1 power. Yeah. Okay, so then go back one trace. And so then this P equals van der Maan inverse S hat can be viewed as a polynomial interpolation of lambda, which is lambda 0 through lambda n minus 1, and S hat. So basically what this means is I have the points lambda I comma S hat I, and I'm trying to fit an n degree polynomial through these n points. And so instead of P for this architecture, we're going to import lambda comma S hat, which is the equivalent polynomial interpolation, into the CNN. Yeah. And so we basically compare this the GCN baselines with the companion CNN, and basically these are the same architectures, except that every time we do graph convolution in a GCN or a TAGCN case, we replace it with a 1D convolutional layer. So that's the only difference between these two architectures. Next. So as you can see, the companion CNN model that we designed performs comparably or better on most graph classification data sets, except for this enzymes and NCI1, where it performs worse. And we believe that this is because the companion model assumes a strongly connected graph. And so that condition is violated in enzymes and NCI1. And so training the companion CNN with lambda comma s instead of lambda comma s hat improves the accuracy by about 6%. Next. And so in conclusion, in the ICAS paper, we show that this GCN and TAGCN convolution is equivalent to a CNN in the GSP companion model with appropriate boundary conditions. And the experiments using a CNN and the companion model achieves competitive accuracies for graph classification. Okay, and we'll take some questions if there are any.
Very nice lecture. Thanks. Very clear, very nice. Just a question for John. So if you're converting a graph network to the companion CNN, how expensive is it to compute the boundary conditions?
So it's the boundary condition is determined by Cayley Hamilton. So it's actually free, right? It's very you just have to do the eigen decomposition, which you have to do anyways. So that's not the problem. The real restrictive part, Shreyas, if you could go back to the lambda s hat. So the real restrictive part is this Vandermonde inverse, right? Because this can get numerically unstable for large n, right? If my eigenvalues are like 2 or 3, and I raise it to the n-1 power, that's very large for large graphs. And so to avoid this, one of the strategies is to treat the p as this polynomial interpolation, but instead of fitting n points to x to a polynomial of degree n, we fit a lower degree polynomial. And this has two benefits. One is it's more numerically stable. If I have n points and I fit like a x cubed or x to the fourth, it becomes a polynomial interpolation problem. Of course, you lose accuracy because it's not exact. But also, the other benefit is then this p becomes band limited, which means that instead of having p coefficients, you would just have like, if it's x to the fourth, you would have 5 values and a bunch of zeros. And so then if you shift it using using convolutional layers, then you probably won't hit the boundary condition. And so by doing that, you can also avoid the boundary condition.
Very nice. Yeah.
I have a little bit more of a basic question. Back when you were talking about defining the local neighborhoods with the K value, right? So to me, the analog and convolutional neural networks is like the kernel size, right? What would be the equivalent of the like stride length in this case? Like, how do you determine how frequently you like calculate those local neighborhoods? Do you always do it for every single node, or do you like try to break it up?
So in terms of the stride length, so you're talking about how in a CNN you can have some spacing, right?
Right, yeah.
That type of stride. So in these architectures, we don't really consider stride length because it's just not incorporated in architecture. So generally you just apply AS and it does the aggregation on all the nodes. That's not something that we really have seen before. It might have been done in work that we haven't seen yet. But basically, as far as we know, this is generally not done. So we don't really consider stride length, though there probably is a way to code it up such that you can incorporate stride length or stride, so you can only aggregate on this node and then you maybe have some jumps, but that's not something that we really see. And so this actually is a very interesting question because the ICAS paper, by showing that the that GCN is equal to CNNs plus boundary conditions, it allows us to incorporate the CNN type of architecture type of tricks like stride or properties like stride or dropout or max pooling, stuff that is very complicated in the GCN or graph CNN world, but becomes very straightforward in the CNN world. And that's something that the companion model allows us to do.
Yeah, and I think just to add on to that, like the closest thing, maybe we can think of stride as being in the TAGCN. So here, maybe we consider the sum over just even values of k. So we would look at the neighborhood, which is just the current node, and maybe we skip the neighbors that are one hop away and just immediately look at the 2-hop away neighborhood. But here, it's still like, there's still probably not a direct idea of stride in graph convolutional neural networks, because the 2-hop neighborhood also, it could include some of the 1-hop up neighbors too. Yeah.
More like dilation rather than.
Yeah, probably. Yeah. I'm not sure if there's a direct thing.
Thank you. And then I had one other question. So you covered graph transforms, right? I was wondering if there's been any work done that you know of for structured state space models, like the Mamba architecture or anything with like really long time dependencies and graph neural nets.
Yeah, I'm not sure of very long dependencies, but right, as you mentioned, the graph transformer has been proposed, and usually those are used when you have like as your representation, your initial representation on the node, you have a very long time series, and you want to incorporate like information from that very long time series in addition to the graph architecture. So I don't know if I haven't seen anything with like Mamba being incorporated with GCNNs, but I could certainly see like you being able to do it. Yeah.
Thank you.
We're out of time, folks. We're going to get kicked out. Thank you very much. Yes. Thank you very much. And that was a wonderful talk. Really appreciate it. So everybody in class who are still here, please give them a hand. And don't forget, these guys are jet lagged. They flew in last night and they are here today at 8 a.m. I cannot be more thankful.